All right, welcome. Today, we're going to pop the hood on a data structure that's, well, fundamental, the linked list. And we're not just going to define it. No, we're getting our hands dirty. We're going to see how to reverse it, chop it up, and even bend it into a perfect circle. Let's get right into it.
So let me ask you this. How do you deal with data that's always in flux? I want you to picture a chain of paper clips, right? You can easily add a new clip in the middle, pull one off the end, or flip the whole chain around without having to move every single other clip. Well, that's exactly the problem linked lists solve so beautifully. They're designed for data that needs to be dynamic, unlike a rigid, static array.
At its very core, a linked list is just a sequence of connected blocks that we call nodes. Now, each node holds two things, some piece of data, and, this is the crucial part, a pointer. Think of it as an address that tells you exactly where to find the very next node in the chain. It's this simple system of pointers that gives the list all its power and flexibility.
Now, when we're working with these, we've got two main flavors. First, you have the singly linked list. This one's like a one-way street. Every node only knows what's coming up next. But then you've got the doubly linked list, and this is a two-way street. Each node knows what's next and what came before it. You know your web browser's back button? That's the classic example in action. That little extra previous pointer is what lets you travel backwards. And trust me, it gives us a whole lot more power, as you're about to see.
Okay, first up, one of the most classic, gotta-know linked list operations, reversing the whole thing. And this isn't just some clever party trick. It's a fundamental test of how well you can handle pointers. Plus, yeah, it's a super common question in tech interviews.
So how in the world do you reverse a one-way street? Well, it's kind of like this carefully choreographed dance with three pointers. We'll call them previous, current, and next. With every step in our loop, the first thing we do is save our next destination so we don't get lost. Then we take our current node and make it point backwards, to previous. And finally, we just slide all three of our pointers one step down the line and do it all over again. It's a really neat little algorithm when you see it in motion.
But what if you're on that two-way street? With a doubly linked list, it's so much simpler. Because every node already knows what's behind it, all you have to do is walk down the list, and for every single node you visit, you just swap its next and prev pointers. That's it. Done. That extra bit of information makes the whole thing a walk in the park.
Okay, let's talk performance, because this shows a really important trade-off. Both ways take what we call ON, or linear time. All that means is that the time it takes is directly proportional to how many items are in the list. Makes sense. But the real difference here is space. The iterative way uses O of 1, or constant space. It's just those three pointers, no matter if the list has 10 nodes or 10 million. Recursion, though, that uses ON space because of something called the call stack. So for big lists, the iterative approach is way more memory efficient.
All right, let's move on to our next core skill, deletion. And this isn't about just hitting the delete key. No, this is more like performing a precise surgical operation to snip out a node while perfectly stitching the rest of the list back together. So the whole goal with deletion is to remove a node without breaking that precious chain. And in a doubly linked list, this is where that two-way street really shines. You basically tell the node before your target, hey, from now on, point to the node that comes after the target. And then you tell the node after the target to point back to the node before it. You're essentially creating a perfect little bypass around the node you want to get rid of.
And this operation is incredibly versatile. You can snip a node right from the beginning, maybe like processing the first item in a queue. You can take one off the end, or you can find and remove a very specific item somewhere in the middle. This kind of flexibility is a huge advantage that linked lists have over more rigid structures like arrays.
Let's just walk through the most common case, step by step. First, of course, you find the node you want to get rid of. Then, you perform that bypass surgery we just talked about. The previous node's next pointer jumps over the target, and the next node's prev pointer does the same thing, pointing backward. Now the chain is totally relinked, and our target node is just an island, totally disconnected. At that point, you can safely free up its memory.
Now check out the performance here. This is really key. Deleting from the very beginning, that's instantaneous, an O of 1 operation. Why? Because you don't have to search for anything, you already know where it is. But deleting from the middle or the end requires you to first walk down the list to find the node, and that makes it a linear time, or O of n operation.
Okay, for our final technique, we're going to do something that fundamentally changes the list's whole structure. We're going to take our nice straight line of nodes and bend it back on itself to form a circle.
The concept here is so simple, but it's really powerful. A normal list just ends, right? The last node's next pointer is null, pointing to nothing. To make it circular, you just take that final node, and instead of having it point to nothing, you make it point right back to the very first node, the head of the list. And just like that, poof, your list has no end. It just goes on forever.
And the algorithm to do this is just as straightforward as it sounds. You start a pointer at the very beginning, at the head. You walk all the way down the chain until you find that very last node. You'll know it's the last one because its next pointer is null. Once you're there, you just do one final update. You set that null pointer to point back to the head. And that's it. You've closed the loop.
And hey, does this performance pattern look familiar? It should. Finding the end of the list is always going to be an O of n operation because you have to visit every single node to get there. But just like with reversing, the iterative method is the clear winner on memory, using that constant O of 1 space compared to the O of n space that recursion needs for its call stack.
So we've reversed lists, we've deleted from them, we've made them into circles. But why? Why does mastering these kind of abstract operations actually matter in the real world? Let's tie it all together. At the end of the day, it all boils down to this one simple idea: pointer manipulation. Whether you're reversing, deleting, or closing a loop, the fundamental skill is exactly the same. Really understanding how to confidently rewire these connections, that is the key that unlocks so much more in computer science. So why does all this matter? Well, first off, these skills aren't just for interviews, though yes, they are absolutely critical there. They are the literal building blocks for more advanced data structures like queues, stacks, and even graphs. But more importantly, mastering this stuff gives you a deep, intuitive feel for how memory and pointers actually work under the hood, and that is a vital skill for any serious developer.
So what's the big takeaway here? You now have the fundamental skills to manipulate data at one of its lowest, most basic levels. You can rearrange, remove, and completely reshape information with real precision. The only question left is, now that you have that power, what problem are you gonna solve first? Thanks for joining me.